are notes which are also there on the e-learning. So you can also open in your machine so that we follow through together. But at the same time, you should be seeing my screen because I'll be highlighting and even maybe calculating a number of things. So if you're not able to see my screen, you can let me know so that we know if there is an issue. So also the chat room remains open, and in case of anything, you can either call or actually comment in the chat room. So someone can comment on the chat room. You can just say yes if you hear me and you can see the screen, so that now we start. Okay. All right, guys have they've already commented. Fine. So I hope everyone is okay. If you're not there in the last class, thank you for joining us for today. However, we had already introduced the outline. Also, we had started. So you can check out the outline and also the notes as far as we had reached last time. So today we are just continuing. In this week, we said we'll be doing revision. So we want to finish this revision so that now we can be good to be able to handle that which we have. So for today, we are going to revise both probability theory, and at the same time, we are going also to revise linear algebra. Then most likely we'll finish on Friday by revising calculus, and those are the relevant applied mathematical knowledge and units that we will need to be able to handle machine learning, deep learning, and related stuff. So if you remember last time, we revised basically statistics, the science of data, and we looked into a few things, the different scales of data, and can have primary or secondary data, etc., and how we measure the spread and the measure of central tendency and the moments of a distribution. By the way, we introduced distributions last week, and we are going now to carry on with the same notion of a distribution today. So very quickly, today we want to discuss probability. You're already familiar with probability. It's the branch of math which studies uncertainty and kind of measures some levels of success or failure as far as events stand. So some of the key things we will talk about are actually things like random variables and distributions. But just for the benefit of those who might have forgotten, we start here. There is an experiment always in probability. There's an outcome, there's an event, and there's a sample space. So actually, an experiment is what leads to an outcome, and an event is a collection of outcomes. And then the sample space is the collection or the set of all possible outcomes. So when you actually run an experiment, you won't get all the outcomes, but actually a domain, a limit on all the outcomes that you can be able to get. And that's going to be important as we move forward. So I will just highlight the key things that we want to focus on in probability. One of those things is a random variable. So very quickly, let's revise this one. It's the numerical description of an outcome of an experiment. So a random variable is always a number, okay, a numerical description. And it depends with how you define your random variable in probability. That will define how the variable will be taking values. And then you will be able to measure the probability that a given random variable is able to take a certain value. To be able to understand this, as many people are normally confused with random variables and all this kind of stuff, we have a simple example here that we will go. So let's say this famous Bernoulli experiment of tossing a coin. We all know coins. They have two sides, the head and the tail. Then let's say you tossed a fair coin. This word is going to be important, a fair coin. So let me just highlight that one. 3 times, okay? So we have done it 3 times. So this will actually be the sample space. These are the set of all possible values that we can actually get when we kind of toss a coin 3 times. Maybe the first time we got a head, then a head, then a head. We can get a head, head, and a tail, etc. Then suppose we're interested in the outcome of the experiment where we want to count the specific number of heads. We are only interested in the number of heads. Then our random variable will read like this. Random variable X is the number of heads. Okay, that's a random variable. So it actually means this random variable, we toss the coin 3 times, we can either get 3 heads or 2 heads and so on and so forth. But the moment you define your random variable, you are going to kind of have a limit. For instance, if I a coin 3 times and my random variable is the number of heads, I'm interested in that, I can either get 0, okay, 0 for no heads. I can get a 1 for 1 head. I can get 2 heads. Then I can get 3 heads, okay? There's no way I can get 4 heads because I have only tossed the coin thrice. That's going to be important. So the point for the random variables is that it can take up a value of 0 when you don't know heads in all the 3 tosses, 1, 2, and 3. That's the math. Good. So that's how we define random variables. They take on numbers. These numbers can either be discrete, like what you have seen, countable, or continuous. Continuous are things maybe 2.5, okay, and so on and so forth. So these are going to determine a lot also. The nature of the random variable is discrete or continuous. The random variable, the value that the random variable takes is a matter of chance. And that's where probability comes in. Probability is the measure of chance. So the questions we might ask here is that, for example, if our random variable is the number of heads of toss the coin, so tossing the coin is the experiment, and this is the sample space. And this is how it's written. Probability that we will get 2 heads. That a random variable will pick up a certain value. And that's like the summary. So now let's go to a probability distribution. Probability distribution is going to be the heart and soul of our study in machine learning. So probability distribution of a random variable, it is a list table or a function. So mostly we'll use a function that assigns probability to all possible outcomes of a random variable. Okay, so the distribution assigns values which are actual probabilities to a random variable taking a certain value. So a random variable takes a value. The distribution says what is the probability that the random variable will take this value. If you understand that, you're way ahead. So what does it tell us? What information does a distribution give us? If X is a random variable, then what is the probability that X will take some particular value, small x, okay? So in other words, all the values in a probability distribution will add up to 1. Okay, so all values, all of them, because probability usually ranges between 0 and 1. Okay, that's like the to be the limit 1, but it will be greater than or equal to 0, etc. Fine, so that's how we define a distribution. So back to our example, how will a distribution look like? Number of heads. You're still struggling. You write here heads, okay, and then you write here tails. This is your first kind of toss. Then you do the next one, okay, like so, like so, heads and tails, and you can continue. Then the final one. This is how our tree diagram will look like. But with advancements, we don't draw these trees. So after you have your tree diagram, all that we'll get here is your sample space. Okay, the outcomes here. Like for example, here, if I have H here, so here I will have 3H or H's, okay, and so on and so forth. So that's the sample space, like this. Then the random variable is defined by the number of heads. That's important, how you define your random variable. Random variable X is the number of heads. That's what we're interested in. Okay, only the heads. We can define other random variables, and then we will get a different distribution. Good. So I can either get 0 heads, 1, and so on. So you see the way the frequency is distributed. The frequency is how many times. So this is how we define a distribution. X number of heads. So 0 heads, we only saw evidence of 1. 1 head, 3. 2 heads, 3. And then finally 3 was counted once, like you see here. So the probability distribution will look like this if we were writing it in the form of a table. So X has the probability of 1 over 8. Okay, it was only seen once, and the total population here is actually the total population is actually an 8. So 3 plus 3, that's 6, 7, 8. Okay, so the total population is an 8. Now, so the probability of getting a 3, okay, the probability that the random variable will take a value 3 is actually going to be 1 over 8. That's what we see from here. So this is how the whole thing of our probability and random variables and distribution is actually defined, and that is going to be very important in machine learning. You're just about to see how we flow with this one. So you can never do modern day, like we said on Friday, modern day machine learning, which can also be called statistical machine learning, basically runs on all these mathematical principles, etc. So now we know what a probability distribution is. What are the most important distributions that we are going to deal with? There are so many distributions. You can even create your own distributions. But these are like the main distributions that you are going to be focusing on. The list is not exhaustive, depending with what you're studying. Some people study computer vision, others study NLP, others study image processing, others study so many applicative areas of machine learning and AI. So it depends with what you're studying, etc. So, but basically, these are like the main distributions. For example, Bernoulli, binomial, and multi-Nulli, multinomial, etc. All those distributions are actually kind of related, and it depends with what they are modeling. So this is actually how we normally write a distribution. The random variable X is, you can see, it's here. This is the random, these are the random variables. And then this is the distribution. And then here we normally write the inputs to the distribution. Okay, so those are examples, discrete distributions that you should take note of. Continuous distributions are these ones, the uniform, etc. Gamma distribution is going to be important. Okay, I will be mentioning distributions as we go by, depending on what we'll be solving, standard normal distribution, etc. Then Gaussian distributions, which I've not listed here, very important also we'll be touching on. And actually, there is a function called a gamma function that is normally defined like this, that we'll also be making use of as we get there. Fine. So let's take some examples so that we are good to go as far as distributions are concerned. So you must remember always in your machine learning problem solving toolkit, you must remember number one, what is a probability distribution? We will be computing probability distributions as we go by. Fine. So consider example is there, the notes are on the e-learning, so you can open it up where we do this together. Tossing a fair coin 3 times. Okay, so it's a fair coin now. What's a fair coin? A fair coin is the coin whereby the head, that's one side of the coin, and the tail, which is the other side of the coin, all have an equal probability of found. So because maximum probability is 1, so we just divide the probability into 2. So the probability of getting a head is 1/2, and we know this, you must have done this already. And getting a tail is also 1/2. That's easy. Every probabilitist must have gone through this, and you're aware of this also. So anyway, 3 times, and noting the number of heads, that's our random variable. You can define another random variable, checking the number of tails, etc. We want to show that the random variable is binomially distributed. So the statement here is that the number of heads is binomially distributed. We'll be making those statements so many times. We'll be saying this data set is hypergeometrically distributed. This column or this target variable is kind of hypergeometrically distributed, etc. So the random variable is binomially distributed. In other words, its probabilities are defined using the binomial distribution. Okay, fine. So we want to calculate the probability, which we already did, that X will take up the value 3. In other words, we will count 3 heads using the binomial formula. So if it's truly binomially distributed, the formula will work. So random variable X binomial is written like this, n theta, the probability of success. And since theta is number of heads, okay, so theta is success in a probability distribution definitions. And then 3 is the number of trials, okay? N is the number of trials here. Then after writing a distribution like this, then a distribution has a formula. For binomial, this is the binomial distribution formula, okay? It's defined like this. The other name for this is the PDF, or the probability distribution function, okay, of a binomial distribution is defined like this. So n number of trials, theta is the probability of success, okay. So in our case, n is 3 and theta is 0.5. So if we plug all this into the formula, we are able now to calculate the probability that X, some things are not showing here on my board, like this one is over, okay, so just check. So this sign here is a sign for combinatorics or combinations. So it can also be written as n combination X. And if you have a calculator, we said last time you must have writing materials and your calculator, you're able to see there's a sign like this one. But also this one can be computed in form of factorials like here. And yes, so anyway, if you compute this one, you'll be able to find 1/8, okay, or 0.125. And actually, that was the probability that we found. Okay, that was the probability that we found in the previous slide here. So you can actually see the number of heads is binomially distributed. So in using all these, we just use instead of the up there, we'll be using the distribution as it is, like you see it here. So this is really easy, and this is a very easy example. So you're not required to cram any formulas or to cram all this mathematics as we're revising so that we apply. Okay, so we are going to apply all these so that you have to know them before you apply them. Then another example is here for Bernoulli distribution. Now, Bernoulli distribution is the same as binomial distribution, where n, the number of trials, is equal to 1. Okay, so we normally move this way. Number 1 is usually the Bernoulli, then number 2 is the binomial. Okay, binomial is the next one after Bernoulli. And then from binomial, you can actually go even higher. There's a distribution that is called multinomial that I use a lot. So in binomial distribution, you can only model things like heads and tails. Bi means two, okay? So any scenario where you have two outcomes and the number of trials is more than one, you use binomial. That's how you know which distribution to use. Anytime you have only one outcome, that's a Bernoulli trial, heads and tails, it's automatically a multinomial distribution. So let's say multinomial is a generalization of binomial. So it means we will just twist the formula for the PDF a little bit so that we are able to accommodate things which are more than two. And that's how formulas are made, and they're not meant to be cracked. We will actually just be applying whatever distribution. So you can also look at this example the same, and the trial is actually just having one. You can even do it with the binomial formula, still the same. Now, where is our interest now? For every distribution, personally, I'm interested in, like what we were doing on Friday, we are interested in number one, the distribution as expressed by its graph or curve, okay? Then said in the shape, okay? The shape of the distribution is going to be extremely important. Remember last time we were talking about how to kind of determine or measure the shape of the distribution. And we talked about skewness, okay, and also kurtosis, okay. The two ways to measure like the shape of a distribution. So here, what I've just done is that I have just plotted the binomial of 3, 0.5. This is how it's written. And the, no, I've not plotted the binomial of 3, 0.5. These are the plots of binomial 20, 0.2, and binomial 20, 1/5. So 1/5 is the probability of success. And then here there were 20 trials, okay? So also here there were 20 trials, but the probability of success is different. So 20 trials is like tossing a coin 20 times. The curve will look like this. You see it here. So you notice beyond 20, the curve just falls to 0 because the trials are 20. So you have nothing more. Like what we were saying, if I toss a coin 3 times, I can never get 4 heads. So beyond n, the curve just hits a 0. And that's important to know. So how is this curve kind of plotted? These are the x, the value of random variables, and these are the p, probabilities. So here you will always have the probability. In the plot of a probability distribution, the y-axis will always be a probability, and the x-axis will always be the random variable, okay? So the probability, if I do 20 tosses, okay, of the coin, the probability that I get 10, if I'm counting the number of heads, so the probability that I'll get 10 heads is defined by this value here, okay? So at this time, I wanted to try and plot the binomial for 3 and 0.5, which is actually very easy. You will have your curve. You have room variables here. Okay, so the maximum will actually be 3. Okay, then you have your probability on this side. So maximum probability is usually a 1. Okay, so I wanted to plot binomial distribution of 3, 0.5, like what you have just seen there. These are the values you will have. These are the values the curve will score. Okay, these are the values it will score. Then you will be able to see the shape of that distribution. Shapes of distributions extremely important. I wanted to plot that one for a minute, then I'll be back. Okay, fine. So I hope you are able to plot. Anyone with questions regarding distributions and this whole story? Let me check if we have anything on the chat room. Okay, everyone seems to be fine here. So we continue. I know all as well. Fine. So now, you know what a variable is, how distributions look like. They have a formula, they have a graph or a curve, and okay, George is asking how we get the success probability. Now, the success probability is normally given, but in this case, we already said because it's binomial and I am tossing a fair coin, okay, the word fair is now underlined, okay. So what's the probability of getting a head and a tail? You only have 2 options, okay? And the maximum probability is always a 1. So what do? You just divide the probability into 2. So the probability of getting a head is a half or 0.5, and getting a tail is also a half. So because our random variable, the random variable is defined, is everything. Because our random variable here defined as the number of heads, So the probability of success is the probability of getting the number of heads, of getting ahead. And that probability is actually a half. Okay. That's how we get the probability of success. Now, we will get to a place whereby the coin is not a fair coin. Okay. That means if it's not a fair coin, maybe the probability of getting ahead is a third, and of getting maybe a tail is 2/3. So there is more chance that I will get a tail than I will get a head. We call that an unfair coin. And given the level of accuracy of how coins are manufactured, there is always a margin of error. So it is not always a fair coin. So the branch of statistics that gets the exact values here is actually inferential statistics, which I will go to, whereby you don't just say that your probability of success is a half. We actually are going to compute that probability of success, okay? And I will get to that in a moment. So for now, I hope that is fine. You can call in if you have questions, but you don't have to wait. I check the chat room. Anyway, look at the shapes of this distribution, because now we're interested in the shape. We are not cram the formulas. We are just going, in case you are coding and kind of creating a model and you need to use a distribution, you just have to check the distribution, check its shape, check things like the mean and the variance, which we're going to talk about in a moment, and then just take a distribution that suits you, and then you are able to use it. But you must know the distributions actually exist, and this is the distribution that I need, and this is the reason why I need it, etc. So for example, here, these are distributions that have been known for many years. One is called Poisson, the other one is called binomial. So if you plot a proper binomial, you will most likely get a shape like this one. This is like the shape. And then if you plot Poisson, you will probably get a shape like this one. I want someone to discuss this curve based on skewness. What can you say about the skewness of binomial? Of a binomial distribution. So here, guys are actually going to call in, mostly those who are there on Friday. Comment on the skewness of binomial distribution. Who goes first? Today we are so many. This is easy. I hope you remember skewness.
It is positively skewed.
Let me see. Yes, who is it? Yeah, Ngugi. Yes, it is positively skewed. Thank you very much. Thank you. I hope you remember skewness. You can just check the notes for on Friday if you are not there. We see that low frequencies are actually here. Okay, so the curve tends to bend that way. So this is the side where we hit very low frequencies or very low probabilities. Now the thing here is probabilities. So you see the shape of the binomial. It is kind of similar to the shape of the, okay. If you also plot Poisson distribution, you will get this. So what message are we passing here? Some probabilities, you can actually see the relationship just by looking at the shape of their curves, okay? So anytime I'm building a model and I see I want something like this, I can either use Poisson or binomial. So it depends. But you see this sign I've put here is that Poisson is approximately equal to binomial, okay? Which rule do they normally use here? Remember, this was n for binomial. N is the number of trials, and this was theta. Theta is the probability of success, okay? Depending with how the random variable is defined. So the rule that they normally use here is that if n is large and theta is small, then you can actually use Poisson and binomial interchangeably. And we have actually just plotted the values here. There are online calculators for computing all this. As we will be computing all this using NumPy and all these other libraries, etc. So sometimes we want to just generate random numbers that are binomially distributed. Okay, we will be doing such things when we don't have data and you want to simulate. I need 100 values that are binomially distributed. Let me give an example here. This distribution that is called normal distribution. Okay, it's one of the most important distributions. For example, the assignment marks students, they are usually normally distributed. The age of students or of people or the age of maybe patients suspected to have COVID-19 is normally distributed. So I can say, because COVID-19 mostly is affecting maybe, and it's fatal maybe in people whose age maybe is above maybe 70, and I want to simulate some data. So I will kind of set my limits, maybe 25, okay, to maybe 90. Then I will generate random numbers between 25 and 90 using the normal distribution. Okay, so the normal distribution will give me numbers. Maybe I want 2,000 numbers. Okay, so maybe I want to simulate the data for 2,000 guys, and I don't have the data. I need age of 2,000 guys that are fixed within the normal distribution. I can be able to do that. We will get there in a moment, in days. Anyway, fine. So my key thing here is just that you understand the importance of distributions, and then we will see how important they are in machine learning specifically. And our focus will actually be on deep learning, and we'll actually be writing these things. But before we write or code anything or load any library, it's the time to recap and be able to understand. So anyway, these are the basics we get from here. The shape of a curve is important. It can tell us a lot. And then the other distributions are like these ones. Okay, so you can look at these ones. These are like the other shapes of other distributions. This is the geometric distribution. You see the way of different values. Okay, so the geometric distribution always looks like this. Okay, and it has a sister that is called negative binomial distribution. So you can see actually they are sharing same. Okay, so the negative binomial distribution is the general form of the geometric distribution. These are called these are examples of discrete distributions. On this other side, we have the famous distribution, okay, probability distribution. This is the normal distribution with different values. You can see the way the curve is behaving, okay? Might look similar to what we were measuring last time. So if we discuss the shape of the curve here, I want someone to just look at the shape and then try to predict, why is this called the normal distribution? Hint, the shape, okay? Just given the shape. So someone to call in, and then we see the views. Why do you think they call it a normal distribution? Mm-hmm.
I think it's called the normal distribution because
Yes.
because it has a skewness of 0, so it's just normal skewness of 0, and
Mm-hmm.
it has like a kurtosis of 3, so that means it's mesochatic. So it's just
Mesochatic.
it's just like plain table. It's just normal.
Okay, okay. Who is that?
Vanessa.
Vanessa. Thank you, thank you. So yes, true. You can actually see the way the curve is nicely distributed. Okay, it's like the values are rising then falling. Okay, so though the skewness, yes, zero skew most likely, and then but the height of the curve kind of plays around. Okay, it rises and falls, but it sticks to the center. Okay, so this distribution, very good, is actually going to be used to come up with other distributions or to estimate. You see the way here you can use Poisson to estimate binomial and vice versa. That's the same trick that guys in probability theory use, made other distributions. It's going to be a very important distribution, by the way, in your data science or machine learning package. For example, all the tables that you have been reading, most of the tables in probe and start class, standard normal table, T tables. Okay, all those tables are just derived from this normal distribution. We won't be reading tables, but as we will be doing calculations. So very fast, there's another example here for hypergeometric distribution. Okay, the reason I put up this one is because if you remember your high school probe and stats, or maybe what you learned in the units, there is usually sampling with replacement and without replacement. Okay, that's going to be important. Say, for example, if I may write on this side. So let's say, for example, I was doing research. This is what I'm doing currently right now. And I have a series of words, let's say keywords. Okay. Okay, fine. Anyway, so I have a series of words, word 1, word 2, word 3, and so on. And I want to kind of model the words, the way these words are picked in order to form a sentence or a document, okay? The reason here I'm going to compute probability of words, it uses multinomial, but I will simplify. So if I pick up a word to form a sentence here, okay? So the moment I'm starting a sentence, the moment before I start, every word here has a probability of being picked, okay? For example, what is the probability I will start a word using the word and? It's very low as compared maybe starting a sentence with the word they. Okay, so different words have different chances of being picked. There is a probability distribution describing the chance of these words being picked. So the random variable there is picking of words, or which word will I pick. Now that's a special random variable because sometimes it might not take numbers. I won't go into that right now. So anyway, the moment I pick this word, okay, what is the chance that I will pick this word again? That depends with whether after picking this word, do I consider it removed from the list, okay, or do I just consider as the moment I pick this, the probability still remains of me picking this word again, etc. You can relate that to the exercise of picking balls from a basket. Looks so a bit simple, etc. So let's say, for example, we have a room with 10 robots. 7 of the robots are red, and 3 of them are blue in color. Both robots can sort given goods in a warehouse, and you can read through these. And suppose we observe the stages. There are 2 stages, stage 1 and 2 of activity. What is the probability that both stages were done by blue robots? Okay. So this one can actually be modeled using hypergeometric. So anytime you are doing or picking balls from, let's say, a basket without replacement. So you can actually compute the probabilities without drawing a tree. That was a hypergeometrical distribution. This is how it's defined. okay? And this is the formula for hypergeometrical distribution. This is how it's normally done. So anytime you're doing things without replacement, there's a chance you will really run into hypergeometrical distribution. So we can actually answer this x equal to 2, where x is the random variable, giving the count of blue robots, okay? That's how the random variable is kind of defined. So this x having the value of 2 is what is going to be fixed here, okay? So what is going to be fixed into the formula right here. Then these are just a series of factorial definitions. We have m here. What does m tell us in a hypergeometrical distribution? You see you're looking for blue robots. So m is the number of, in the total population, how many blue robots do I have? There are actually 3. This is how hypergeometrical defines it. So this computation here is actually 3 combination 2, okay, which you can calculate using your calculators. 3 combination 2 multiplied by 7 combination 0, and then divided by 10 combination 2. So 10 is the total number, the total population of robots here, okay. And then, yes, so that forms your large N, okay. Your small n is the sum you're picking from the population. I only need to see 2 pages, so I'm just picking 2 robots. And the explanation goes on and on. So n minus m, you'll actually get a 7, etc. So bottom line, replacement. I actually drew a small tree diagram, not visible for me, but for you it should be. So let me see. I actually have to see this one. I don't know if I have it open here. Yes. So all the way down. Yeah, so yours looks like this, and you can actually see down here. So when you're doing without replacement, when you're starting the first sample, the probability of getting a red is 7/10. 7 is the number of robots which are red, 7/3/10. After picking a red robot, the probabilities change immediately. So now the probability of picking the next red robot is 6 because you've already picked 1/9 because 1 robot was already removed here. And the probability of picking a blue robot is 3 because you never picked over 9 because already red has been picked here. That is going to be so important. So the probabilities actually look very different, as if different from what I will do if I was picking without replacement or with replacement or whatever we are doing right now. So anyway, fine. That is an example of a hypergeometrical distribution. So if you are doing that with replacement, it will be a binomial distribution, okay? And you can actually draw the tree when you are picking with replacement. So the probabilities won't change. So 7/10 here, 7/10, and then I pick a red robot, and then the probability of picking another red robot still remains 7/10, etc. But without drawing all this, as we will just be computing things using the distribution and its formula. And that ends our introduction or our reminder to distributions. Any other question on distributions? You will understand as we encounter more. So another key thing you have to get in machine learning before you do machine learning is what is called conditional and joint probabilities. This is the next important aspect. So I'm going to explain these terms which usually confuse people using a tree diagram. All of us know tree diagrams. We loved them back in the days. So what an opportunity to reuse them. Now, let's say we had only two events, event A and event B. Okay, the probability of event A occurring, which we write like this, can be captured by the tree diagram. Then the probability of B occurring also like this. So anytime you only have the probability of a single event, okay, that is called marginal probability. Okay, that's a marginal probability. Marginal probability. Then let's go to conditional probability. What is this guy who is so important? Now, after event A has happened, then event C happens. Okay, so the conditional probability is the probability that event C happens given that, that's where the condition is, given that A has happened. Okay, so A must happen first for C to happen. So here is where we actually have the conditional probability. The probability that event C happens given that A has happened. We normally write that one like this. Probability of C given A, okay? Or probability of C condition A, okay? So this one just says, what's the probability that C happens after A has happened, okay? That's a conditional probability that can actually be captured by a tree diagram. Good. Then finally, the joint probability. Okay, this is a term also you're going to meet. So joint is also easy. You can see here, joint probability is like just saying probability of A multiplied by probability of D happening. Okay, so it's A intersection D, and all these are joint probabilities, all of this. So in joint probability, we normally multiply. That's why you used to multiply along this line. You are finding joint probabilities back in the days. So that's a joint probability. So in joint probability, we usually multiply. Okay, we usually multiply. But now from that definition, we are going to establish some of the most important formulas of statistical machine learning. Now, because the joint probability is multiplication along these lines, and along that line, we do also have a conditional probability. So there is another way of defining a joint probability, which I have outlined here. So take note of this. So the marginal probability times the conditional probability along that line is actually what a joint probability is. So actually here we can just say probability of B, because B occurred here, of given B, okay, C given B. And that's how this simple diagram is used to explain all the three important probability terms that every machine learner or a data scientist should actually know. So you can look at this diagram, then understand these three terms: marginal, conditional, and joint, okay? Just the way they flow along this line. So now, let me now go down here and now discuss bias theorem, Theorem 1776, the most important theorem that needed to be established for modern day machine learning to work. So what is Bayes' theorem? Because we will have Bayes statistics and actually Bayes machine learning or Bayesian models. So the Bayes theorem is a novel of calculating conditional probabilities of hidden data. And I'm going to explain and actually to illustrate. So because my board is not showing this thing clearly, so let me just open also the PDF down here. So this is what you should be seeing. So we have said from the tree diagram, you can see I can easily get probability of A, which is the marginal probability, and I can also get the conditional probability of C given that A has happened. Okay, so this is defined along this line. Probability of C given A. Okay, it's written like this. Now, Bayesian or Bayes theorem can be used to calculate probability. I can't write here. Probability of A given C. So you see, actually, what you have is probability of C given A. So let me just write here, and you can have this in your notes. It will help you a lot. People struggle with this, by the way, and I want you not to struggle once we start. So probability of C given A, that one we have, okay, that one we do have, is not equal to probability of A given C. Okay, these are two different probabilities. This one is found in our tree diagram, okay, or we have it or it's given to us. This one was not able to compute for years. This is what we call hidden data in this case. So Bayesian theorem is a way to calculate this conditional probability. That's what Bayes theorem gives us, a formula to calculate this. Okay, so that's what you're seeing here. I have this. With respect to that tree we have up there, it depends with the tree you have. The formula for getting this according to Bayes is actually that. Okay, and that formula is going to be super important as we go by. So probability of AC is given by probability of A multiplied by probability of C given A, which we have, divided by the probability of C, okay, the probability of C. But how is the probability of C defined? So the probability of C, we have two C's. We have two C's. Let me go back here. We're just deriving a formula. Don't cram, but just know Bayes theorem. By the way, you have to know this one. So we have two C's. There is C, which is here, and then this C, which is here. There are two ways to get C. Either I take probability of A times probability of C given A along this line, or I take probability of B multiplied by probability of C given B, okay? So time you have two like this, remember we normally multiply when we go towards that direction because you are getting a marginal probability, we multiply. But if I was to get the total distribution, I will add. So if I add this plus this plus this plus this, I must get a 1, okay? In other words, I like explaining the whole of probability just by this diagram. So this is a distribution. Okay, what we have here is a distribution. Anyway, so there are two ways to get C. So I have this marginal probability and then this marginal probability. I normally just combine them using an addition. Okay, so it's the law of probability that says there are two ways to get C. This or this. So anytime you have an or in probability, we normally add. Anytime we have an and, we multiply. If you revise, you will get to see that. So basically, we are just using, so probability of C is given by that and that. That's how we arrive at the Bayes theorem. So this is called Bayes theorem, a way to get conditional probability in this form. Okay. So this is Bayes' formula for two events. Okay, so you notice here we just had two events. The first event, I either get an A or a B. The second event, I get a C or a D. Deriving Bayes for three events is something I don't want to do here. And four events, by the time I get to 5 events, we are now at 106. I will have 6. By the time I get to 6 events, I will have 6 divided by 2 students remaining, etc. Anyway, there's no need to go towards that direction. We rarely get there. So anyway, just have the Bayes formula for 2 events. For 3 events, it might look like this, but we will be coding, not doing mathematics on paper. So it doesn't hurt. We just know how Bayes, what it does. That's the first thing, and how it looks like. So example, the rate of young persons getting sick from COVID-19 is only 1%. The young people, it depends how we define young. And the chance of young people contracting the virus, okay, is 10%. From all young people, 6% of whom contract the virus, they actually fall sick, okay, or they fell sick. This past data, maybe. If a young person contracts the disease, what is the probability they will get sick? So you only see, we might want to calculate this one. What is the probability that a young man who is infected with COVID will actually get sick? Because there's some young people affected, but they won't get sick. It won't affect you. Studies are saying for some people it's just like a flu. You just walk around and something like that. So we can actually not be able to get this until we have Bayes formula. And you are encouraged to draw this tree diagram so that you appreciate what Bayes did in 1776. Let the probability of being sick be PS and the probability of contracting be PC. Okay. So the probability S given C can be computed by the probability of C given S, which we have, which is 0.6, okay, 0.06 times probability of S, which is contracting the virus, 0.01, and yes, getting sick, that is P of S, probability of getting sick is 1%. That's what I've captured here. And the probability of contracting the virus is captured here. When you do this, you actually get 0.6% chance that if a young person gets COVID, they will get sick. If that were true, then this is quite some number, because it depends with how many young people actually. So 0.6 of 0.6% of 100 people is different from 0.6% of a billion people, etc. Now, Just follow through these ones. Don't struggle much on how do I calculate this? What will I write in Cat 1? That's not the point. The point here is to understand bias before we start doing our machine learning thing. Now, here is what you should capture. This is AI captured in one slide. Machine learning captured in one modern day machine learning. Now, given Bayes' theorem, here is how we understand modern day machine learning. Okay. The probability of A given C, which can be computed using Bayes, is now going to be called the posterior probability or posterior distribution. So you will hear guys talking about posterior distribution. The probability of A, the marginal probability of A, and I've redrawn the tree here, is going to be called the prior. You will hear us and you will see and you'll actually write code to compute the prior. The probability of C given A is called the likelihood, and this we will do a lot. And the probability of C, with respect to this tree, by the way, that's how we are simplifying, is going to be called the evidence. Now, the evidence is actually the data we have. Okay, it's actually the data that we will have. And this is what we normally do in supervised learning. Okay, we want to find the probability of a class given the data. Okay, for example, what we are doing to determine whether a car is fast or not, if you remember that, if you have a photographic memory, you don't even need a photographic memory to remember the task we were doing. In the tree that we had, decision tree, we wanted to know whether a car is fast or not. Those were the classes or the labels or the target. So if I have a new car that has an engine which is not heavy and consumption is much, etc., those features, given the data, what is the class? So actually, we normally compute, then we have different candidates, then we are actually going to pick the class with the highest probability. So what is the probability that this is fast? That's what is normally computed. So it is a probabilistic system. So like half the algorithms in machine learning, they are going to be probabilistic algorithms that are actually inspired by this formula. So Bayesian theorem becomes extensively important as far as machine learning is concerned. We will return to this. For now, just have this model. This is normally, in a nutshell, what we do. In machine learning, you are given a data set, the evidence, okay? Then you want to determine the class that this data belongs to, okay? And actually can be run this way. Now, doing machine learning using this formula itself is theoretically possible, but practically not possible. The problem here is that we are going to say that Bayesian theorem, as it stands like this, is not computationally tractable. When something is not computationally tractable, it means that you will get to a point where by tracking some things, you will lose track. Let's say we start drawing a tree, then the branches are so many that we actually say, no, forget, this tree is getting too large and it's difficult. So what happens when you try to do machine learning like this? But theoretically, you should end up into what you actually want. But now we are going to take this by and actually create so many models out of it. So that's where I want to finish revision for probability. But before I finish, I have some things to mention to an event that a random variable will pick a particular value in the sample space. That's the mathematical definition. But now, apart from the probability distribution, there's a probability distribution of a random variable, like what we have looked at up there. Then there's the probability distribution of a distribution. Very confusing. You have to let that sink. So there is a distribution of a distribution. Okay, and a distribution of a distribution is going to be important in machine learning, like we are going to see. So here are a few examples that are actually going to be used. Okay, so when one probability distribution can be used to model a probability distribution, another probability distribution, that's where you find this term called conjugate prior is found. So you will find some famous pairings like these ones. One distribution is paired with other distributions. So here we are saying beta distribution is the conjugate prior of binomial. In other words, it models the distributions over binomials. We will understand this as we go by. The Dirichlet distribution is the generalization of the beta distribution. So because from binomials, we usually move to multinomials, okay? Then we say the Dirichlet distribution is the conjugate prior of multinomials, and we are going to use this a lot. Gamma distribution is the conjugate prior of Poisson and other distributions here, like you can see here. So gamma distribution sits at the middle. Then it can be used to model log normal, exponential, Poisson, and the normal distribution. Beta distribution sits here. It can model all these distributions. One of the things you can do with a distribution of a distribution is found in the question that I was asked a moment ago. So I go all the way back here. So let's say we want to model, we know that heads and tails, they are binomially distributed. And let's say it is not a fair coin, okay? So we can't say head is 1/2 and tail is 1/2, okay? So here is the tricky question I can use to explain a distribution of a distribution. If I say the probability of getting a head is 1/2, so I can ask, what is the probability that the probability of getting ahead is 1/2? Maybe the probability that the probability of getting ahead is 0.9, which means of getting of ahead being 1/2 is 0.9. This means we are 90% sure that this head has the probability of 1/2. That is confusing. So there's probability of a probability helpers. So mostly we don't say the probability of getting ahead is 1/2 and the probability of getting a tail is 1/2. No. When we want to model this experiment, we know we can model heads and tails using binomial, but it's not always a fair coin. There's always error in making coins. The coins are not fair. So the distribution to model the probability. So anytime you're modeling the probability of success, that's where now this is going to apply. And machine learning is going to be interesting in solving this kind of problems. So we go all the way down here. So because now we have already made a statement here that the beta distribution or beta distribution is the conjugate prior of binomial. So we will model heads and tails using binomial, but we will model the probability of success using data distribution. And that we are going to practically do. So there is a distribution of a random variables that assigns probability to values that are random variable peaks. Then there is a distribution that assigns probability to probabilities, and that you can just have it noted somewhere. We will come back to that. Finally, all probability distributions have, these ones you already know, they have a mean and a variance which you are going to use. They have a density function that are defined by all those you have seen. By the way, those curves that we are drawing, they are just the density functions, like for the normal distribution, etc. It's a PDF. You can check out all this. We'll be applying them. And all probability distributions, they have formulas, okay, which we are not going to cram, but you're going just to be checking. If I need a binomial, I'll be checking its formula. There's a formula for gamma, for log normal, exponential, and many other distributions that are derived from statistics and calculus, etc. Fine, enough of probabilities and distributions. Bottom line, Bayes theorem and distributions, and then distribution of a distribution. Don't forget these terms. These are the most important terms. The posterior probability or posterior distribution, the prior, the likelihood, and the evidence. So most likely we will be trying, so machine learning is basically trying to find the posterior distribution. You see, this is PAC that we were trying to find there. So mostly we'll be calculating whether we know it or not. Sometimes because we are not doing the math way, sometimes it's hidden inside nodes of a neural net and we don't even care about the formula. But basically this is what the model is doing, trying to discover a posterior distribution. This distribution could be any. It could be log normal, it could be binomial, it could be hypergeometrical, or any other distribution that has not been discovered by anyone. Okay, so it is trying to find mostly posterior. Sometimes we will be looking for the likelihood. Sometimes we'll be looking for the prior. But always we will be having the evidence. Okay, the evidence will always be there. And that's how we wrap it up on distributions and probabilities, etc. And the key things that we just have to pay attention to. Any concern on distributions and such? All you have to do now is just to always expect that you will be seeing things on distributions all the time. Fine. So now we close the chapter on probability and distributions. Okay. So close this one. I don't need it. Yes. And the next thing that we are meant to revise, we finish early. Let me see. Now you can switch over to linear algebra. Can take maybe a 5-minute break, then we return. You can grab something from the slides will remain here. We take a 5-minute break. My clock is not always okay, so I guess it's 12:41. Okay, fine. We'll return at 12:46. Okay, fine. So we are back. The agenda always remains here. We introduced machine learning. We revisited anyway because we had already introduced in AI. Now we looked at statistical versus classical machine learning. That was on Friday. Then now currently we are understanding statistical machine learning by revising some key mathematical units or knowledge that we actually need. We know, but we are just kind of doing a recap. So far we have looked at statistics, probability. The next knowledge that you need in machine learning is actually linear algebra. So we want to revise linear algebra. This is the next kind of sub agenda. So you can open up these slides. Here we need some knowledge. We need to revise scalars or scalars, vectors, matrices, and tensors, matrices and linear systems, vectors, eigenvalues, and linear independence. You must have looked at this in your linear algebra class or whatever it was. So I'm just going to revise. Very good. So we start here. Scalar or a scalar, we'll call it a scalar. It's a single value, okay? It's usually a single value. So for example, maybe a 2, okay, or a 3. Get my pen. Yes, maybe a 2 or a letter B, okay? Usually a scalar, just a value. And etc. Alpha, etc. Then a vector is a one-dimensional array of values. It can be a column vector or a row vector. Okay, so could have something like this. Maybe 1, 6, 5. Okay, vector. So this is a column vector. This will be the most common. Then we have a matrix, which is actually a two-dimensional array of numbers. We all know a matrix. Maybe 1, 3, 9, 5, 6, 0, 4, 8, 3. The matrix. These are 3 by 3 matrix. Where mind, then another matrix is on top of it, etc. I can't actually draw it here on a 3D space, on a 2D space. So a tensor is a 3D plus. Okay, it could be 4D, etc. Good. That's why they call their library TensorFlow anyway. So fine. So let's start with the matrix. These are the important things you should know about matrices. So you should revise about matrices. Number one is the order of the matrix. So a matrix has rows and columns. Okay. We can say it's a M by N matrix. It's a rectangular array of numbers. Okay. And then there's the order. Here, we will call the order of the matrix in machine learning the shape of the matrix. It's highlighted down here. So this is like matrix A, looks like this. Okay, it has rows and columns and elements in it. Aij is called the ijth element of A. Okay, good. These are the columns going, these are the rows going that way. And then these are the columns going this way. So there are some special matrices that we will use that you should know. Number one is a square matrix where the number of rows is equal to the number of columns. Then there is a symmetrical matrix AT means the transpose of A. Transpose means that you just interchange. The rows become the column and vice versa. That's the transpose of a matrix. If the transpose of a matrix is equal to the matrix, we call that a symmetric matrix. So symmetric is a geometrical term. It means that even if you twist that matrix, you will still have the same one. Then a square matrix, which you have seen here, is called a diagonal matrix if these elements are equal to 0 for this property. Okay, so upper triangular defined here and lower triangular defined here. In other words, upper triangular, if we had this as an upper triangular matrix, it means that we will only have values up here. Okay, this will be a 0, a 0, 0, 0. Lower triangle like that. But it to be a square matrix. You see here, I can't even highlight elements in the diagonal because it's, no. So we call that an upper triangular matrix. Then finally, a diagonal matrix is called an identity matrix if Aij is equals to 1, like this. So for a by 2, the identity matrix will look like this: 1, 0, 0, 1. Okay, this is the 2 by 2 identity matrix. It's going to be an important matrix for us. Then let's go to the most important part. There is the inverse of a matrix. Okay, the inverse of a matrix. Before I forget, everyone must watch this. Okay, it's compulsory. There are some things I want you to get there. So please, after this class, before you forget, click on this link and watch that YouTube tutorial. Fine. So the inverse of a matrix is also going to be important, and any matrix is called non-singular or invertible. Okay, if it has an inverse. Okay, so a matrix which has an inverse is called invertible. We can get its inverse. Okay, the opposite is true. Some square matrices do not have inverses. So these are the matrices that are called singular. So a singular matrix is a matrix with no in. Okay, that one you should take note of. A singular matrix is a matrix without an inverse. Then you should also note we can only compute inverses of square matrices. Okay, so if you have a matrix not a square matrix, 2, 3, 5, 6, 1. Don't even waste time computing an inverse. It doesn't have one. So you can only have inverses of guys like this. Okay, and actually the inverse of this is this. Okay, it's actually here. And the inverse of matrices is going to be extremely important in machine learning. Fine. So how do we get the inverse of a matrix? First, we have to discuss the determinant of a matrix. So what's the determinant of a matrix? Determinant is very difficult to explain. So I normally say the determinant is the scaling factor. Okay, the determinant of a matrix is the scaling factor. I will explain that in a moment. Or even better put, it's the product of all eigenvalues of a matrix. We'll get to that. But first, some few tips on the determinant of a matrix. Determinant entity matrix is 1, okay, because ideally the determinant, the identity matrix does not do anything. What do I mean by doesn't do anything? Why do we need matrices? The idea here is that a matrix is going to do things like the following. We have things we call vectors. Okay, this is a 2D space. Okay, so different pen, let me see, blue pen. This is a vector. Okay, vectors have a direction and a magnitude. Let's say here is this is the x-axis, so let's say 1, 2, 3, and then this is maybe also 3 or 4. Okay, this is a vector. Now, vectors are our concern. That's what we do. We will use vectors to represent so many things. We'll get there. They can represent words, they can represent pixels in a picture, they can represent so many things. We'll be representing so many things using vectors. Now, what matrices do is that they do things to vectors. What are those things? For example, a certain matrix rotate this vector, okay, with a certain angle, and then it becomes now maybe a new vector. So let's say it's rotated, and then we find a new vector here. Okay, matrices do that. Sometimes a matrix just rescale the vector. Okay, so that you vector. Okay. So this is like rescaling, and then this is like rotation. So anytime you multiply a vector, okay, like this one, vector 3, 4, say with a matrix, say matrix 2, 0, 0, 2. Okay, I hope you remember how to multiply matrices. 2 times 3, which is actually 6 plus 0. So the answer will be 6. And then you usually multiply this like this, then this like this to get the second element, 0 plus 8. You see, when you multiply a matrix with a vector, you just get a new vector, okay? So a matrix times a vector, you get a new vector. So matrices actually transform vectors. If we may summarize linear algebra, matrices transform vectors. That is going to be extremely important. In our neural nets, what you actually have is a matrix of weights. Okay, weights matrix. Then the inputs, whatever the inputs, words, images, COVID-19, images of the lungs, and the maybe images of the brain, medical image, whatever the features, they can be represented as vectors. Okay, and this is going to be our model. How do these weights transform this and what are we getting on the other side, etc. So when I say no scaling effect, it means that if you take an identity matrix and then multiply it, a given vector never change. Okay, we can try it here. So vector 3, 4 multiplied by the identity matrix of order 2. Okay, if you multiply this, there will be no transformation, no change at all. 1 times 3 plus 0 becomes 3. Okay, when you multiply, you will still get the same vector. That's what identity matrices do. So that's why I define the determinant as the scaling factor. I even remove scaling. It is a transforming factor. Okay, it will tell us a lot whether this matrix will rotate this vector or enlarge this vector, and so on and so on. so forth. So if you multiply a matrix with an identity, you just get the same thing like that. Okay, fine. So determinants can only be found for n by n matrices. Okay, so you can never find a determinant for a matrix which is not a square matrix. So you can only find determinants for square matrices. You can try, it won't work. A singular matrix S is a square matrix with no determinant. Okay. So the same way we say a singular matrix is a matrix with no inverse, is the same way we say it is a matrix with no determinant, because there is a relationship between determinants and inverses. Determinants are calculated using the cofactor expansion algorithm, which is computationally expensive. Okay, we look at computational expenses in learning theory. But now, how do you compute the inverse of a matrix? First, you need the determinant. Okay. Then from the determinant, you can compute the inverse. You must know how to compute inverses of simple matrices. But you must note there is no easy way of getting determinants of matrices above the third order. So if I have a 4 by 4 matrix, it's going to be so expensive to compute its determinant, and so on and so forth. But let's rush through how to compute determinants, then we see how our time will be looking. So this cofactor, I want you to revise. I know you already did this, but it's going to be extremely important. So the cofactor method is asked to compute the determinant of this matrix, okay, using the cofactor expansion method. There is actually how you can be able to flow. Done some which I just took a picture because it was late in the night. So you will actually be able to flow using things explained here. You are either explaining things in an easy way or a mathematician. Okay, it's either one of those things. This is the mathematical explanation. You can follow through it, but it's actually very easy. You just need to form a submatrix, okay? Then you need to take note of the signs. So very quickly, get your places to compute. You remind yourself how to compute this determinant. Determinant is written like this. The determinant of A is written like this. So if you want to compute the determinant using cofactor expansion method, you can do it with any row, by the way, or any column. So I chose to use the first row. So you will pick the first value, -2. Okay. Then you are going to form what we call a submatrix. Okay. But for us to be able to take note of the signs, we are going to multiply -2 by something here, by -1 raised to power I plus j. I plus j. What is I plus j? I is, this is in the first row, so the first element, I'll write it as A, is in the first row and first column. So this is I and j. So it will be -2 multiplied by -1 squared. That's why you see me squaring here, multiplied by the submatrix. So how do you form the submatrix? The submatrix by the determinant of the submatrix. I'll write it like this. So to form the first submatrix, you will cancel row I, this one, and column J, this one, depending with the element you're dealing with. So since I'm dealing with this element here, cofactor expansion says that just cancel that row, that column. Then my smaller matrix becomes 2, -1, -1, 1. Okay. Then I move to the next one because I'm using this entire row. Okay, I take 3, so I will add that one. That's why you're seeing a summation here. There is a summation here. You're seeing the way we compute the determinant. This one you must know because we will not repeat it. Now we'll just be moving. You take the value 3, then you form the submatrix, cancelling that and cancelling that. Then you'll be able to get it as you go forth. Okay, fine. So if I may clear that one. Column 2. So I will ignore row 1, column 2. So my smaller matrix will actually be 1, -1, and -2, 1, like that. So this one means the determinant of this smaller matrix. And we all know how to compute the determinant 2 by 2. That is called the base case of this algorithm. Okay, it is 2 times 1 minus -1 times -1. Okay, then you'll be able to get the value there. So that's how you compute the determinant of this entire matrix, and then you actually are able to get a 6. So you can follow through the computations from the slide, and then from the determinant now we are supposed to get remember the aim is to know how to compute the inverse of a matrix. You have done it, so it's a revision. Then after you have the determinant, so before we even finish, I want you to try and compute this one. Okay. So let's say you have this matrix. I know you can see my screen. I just pick anyone, any matrix, 6, 3, and say 5, 8, 12, 2, then 2, 1, 3. So just clear this one. We have a smaller value here. Let's say 4. Matrix M, compute the determinant of this matrix. Okay. Then you can tell me the value. I'm also computing, by the way. So once you're done, you tell me. Then we'll see if we still have time. We'll continue. If you're tired, we'll end it. Then we'll continue in the next session. But I still want you to try and capture this one. Okay, fine. I have my answer. Anyone who has found an answer? Mm-hmm. Calculators running. Yes, 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 yes. We'll be computing really fast, by the way, and even coding faster. Nicole. Nicole, how are you? Nicole, can you hear me? Nicole has ran away or um, not there. Okay. Mhm. Anyone else who has found this? Walter, what have you found? You can hear me. Mhm. Helen, I know you now, you can hear me. What have you found? Okay, guys are telling me they are still computing. Please learn we'll be computing a bit fast, so always have your will be this is warm up. We have not yet started. Yes, Stephen.
Hi,
Hi.
I got zero.
Yeah, Stephen has gotten 0, and my friend Kulthum also has 0. Stacy has 0. Yes, yes, yes. In fact, answers are flowing like a flood. So yes, guys, I've also found 0. Uh, Thank you very much. Thank you. Someone to interpret that. What does a determinant of 0 mean? According to just the small thing that we have discussed. Anyone who can try. You see, now we will be trying. You see, now it's fourth year. We'll be trying to understand what these things actually mean, as opposed to just computing and using it. What would you interpret a determinant of 0 to be? Any thoughts? Okay, you guys are saying the matrix is singular, and yes, the matrix is singular. That is Sam actually confirms that. Yes, it's very true. It means, you see now, if the inverse is 0, actually, no, if the determinant is 0, there's no way of going to compute the inverse, because the inverse depends on the determinant. So actually, it's 0. So we'll just be doing things like those ones. If you are doing your building your model and you have matrices with the determinants of 0, we just know this matrix has no inverse, and there is something we will tie to that. A matrix having no inverse will actually mean something for us. So that's basically linear algebra in a summary, doing things like these ones. So this thing called cofactor expansion can be used to get the matrix. So Edmond is saying something here. Rows and columns are linearly independent. Yes, I will actually get to linear independence. I think I will get there on Friday, given the time. I know some people might be tired. That's true. That's true. I'll actually be talking about it. Dependence. No, I will tell you something on that. So, yes, finally. So, once you have the determinant, and we can do the same, by the way, for now, the problem with a 4x4 matrix is that to 2x2. And in a nutshell, just know that the method is used to compute. So 2 slides and then we are done. There is something called now the adjoint. Remember, we have not yet computed the inverse. So before we compute the inverse, or are able to compute the inverse, first we get the determinant. Okay, no one is going to ask you this in machine learning. This is knowledge we are going to apply. Then we have the adjoint. Okay, so what's an adjoint? It is another matrix that is created from the matrix. Okay, in this way, the examples do it better. Okay, this is how an adjoint looks like. Okay, so if I have 3, -2, 1, you are already seeing this. Okay, create this. It's the same way. So when I'm dealing with the first element, which is 1, 1, okay, I will ignore these and that. Okay, then this forms my smaller matrix, which you're actually seeing here. But we normally start the first with a positive sign. The best way to track the signs, because it might change, is just by saying -1 raised to I plus j. Okay. If -1 is raised to even powers, like what's happening to my pen, -1 being raised to even powers, like 1 squared, it will be a positive, and -1 being raised to odd, like 3, it will be negative. So here it will be positive, negative. That's where these signs actually happen. So this is the adjoint of this matrix. Okay, you fill up the columns with smaller matrices like this. Then this adjoint is, so remember when we write this, we are saying the determinant of Okay, so after I write all these, I compute their determinants, I fill here, then this is now the adjoint of the matrix. So finally, now you can compute the determinant multiplied by the adjoint. Okay, so this is the formula for getting the inverses of all matrices. And it's going to be important because this is how we are going to solve linear equations. If I have a matrix like this one, then I have unknowns, okay? X, this is a 3D space, Y, Z. Then I want to get some values, okay? Or let me say, let's say, I already know these values and 6. Just a moment, someone raised their hand. So to be able to get this vector, remember in maths, just by like taking this to the other side, okay? And anytime you take things to the other side, actually define their inverse. That's where the inverse matrix is going to be important. Okay. So we are looking for you must be the entire linear equations. They are normally written like that, and you can read ahead and revise. This revision, we might get to a place whereby we can no more continue the revision Friday, and then now we can be able to start. So please revise what can be revised, so that I'll just go through it quickly. Then we'll be able to start with machine learning theory, and then also we start our first task, coding, etc. So you can look at all this, how to solve linear equations using Cramer's algorithm. Okay, and it's just using what we have just pointed at. So let me check the chat room here. Very fine. Issue with IBA. Okay, that's different. And then someone was raising their hand. I don't know. It's gone. Let me see here. Okay, anyone with a question apart from attachments? The rest is revision. Okay, that's revision supposed to be applied, not there in the cards, not there, etc. But it's there in real life, and it's there in the algorithms that you are going to model or develop. So on Friday, we'll finish just revising this one, linear algebra in general. We look at vectors and matrices and how they actually influence each other. So all the way down here, you can read ahead, vector spaces, etc. And after I finish this one, now the most important math unit is actually now going to be calculus. So I must revise differential calculus on Friday. And now on next Monday, I will now be free now to start on the real stuff. Now here, remember, you must watch this one. This guy is discussing some good stuff about matrices. I want you to watch this one. Then also down here, as you read through this one and do your own calculations as you revise, please also watch these ones, the way this guy is calculating linear independence and dependence, okay? And what actually is linear dependence and independence, okay? It's going to be important. And yes, just actually taking care of ourselves. Then finally, there will be small assignments on these ones, but guys, I find these documentaries, YouTube originals, the first two, to be so interesting and actually great, especially So this one just watch as you relax. And then I will also set up some few questions which will act as assignment one. But the questions will be titled Applied Mathematics for Machine Learning. Okay, that's usually the first topic in any machine learning book. You will just be applying all this as you calculate, and that will be part of the first assignment. So, but in CAT, we won't be, there will be something different to do as I go. We'll just be applying and coding and actually understanding. So I guess for today, up there, Friday we'll be meeting. You can, by the way, installing all this. Yes, Rose Ann.
Finish.
Okay. So, but I'm finishing. It's like a parting shot
Oh,
now.
then
You can just ask it. Yes.
In the IBA report,
Yes.
are we still supposed to get the signatures?
Okay. That's going to be dealt with on a case-by-case basis. Discussions are still ongoing.
Okay.
There is something that is supposed to be confirmed to the faculty board. That's why we have not yet officially communicated. But now this, in my opinion, because it's not yet still official, it might be on a case-by-case basis. Because, but I think in IBA, we were suspecting we won't have those incidents. Because some of you are working from home, some organization home, I don't know. But if your report was not signed before that, we'll be trying to deliberate on the way forward and maybe a different way to kind of validate that you actually undertook the attachment, etc. We might maybe request a letter from your host supervisor. They can do it maybe if they're working from home. They can do it for you, then send it over. Then you can, we were thinking of digital submission of reports, not digital, actually soft copy, but not yet confirmed. Those are some of the things that we are still discussing. But for now, if you don't have a signature, you can maybe try work on a letter, okay, that they can do it remotely because now it's risky, guys are not meeting. And then they can actually share it with you, and then you will make it part of your report, maybe in the appendix. So, but if it was already signed, that is okay. You don't need a letter, etc. The issue here is that they normally just need a way to verify that actually your host supervisor certifies that you actually did the attachment. Is that a bit helpful?
Yes.
Yes.
Yeah, a submission link on
Yes.
like is the submission link like permanent, like we're supposed
The submission link, you have seen it.
Yes.
For us. So actually, the submission, I did set dates, but we also have the communication, the message that we wanted to share with you guys. But for a moment. But communication official, I will be sending very soon. Very soon. So someone will communicate to you. For ICS, I think Dr. Wong said he will communicate. Which is you, IoT, we work in the same office, so he said he'll communicate to you guys, but still not yet official. That's why we have not yet communicated. But the way forward will be communicated. For now, I will just say have all that you can get as letters, because we don't know what will actually be decided.
Okay.
Yes, we have Isaac on the waiting, or it has been
It's okay.
answered.
It's okay. Yeah, the
It's
question has
fine.
been answered. Yeah.
Okay. For those of you who are in the final weeks and then lockdown was declared or it got too risky, we are also considering those, because I know by now contracts have expired, etc. So it was a pandemic. No one was well prepared. So still, you don't have to be afraid. We might think of a way to rationally deal with those hours, but official communication also will be flowing. So for now, the most sure thing I have right now is that reports still will be required. Be on the safe side, by now you should maybe have your report ready. Okay, there's a format there I put up on that e-learning page, and then just be waiting for the next communication, having all that you can actually have. I think that one try to help a bit. So before we finish, a minute or so, Caesar has a question. What if you have a hard copy signed and stamped? How do you submit it? Okay, fine. So this one again is the next thing. Because if you have a hard copy, it means already still your soft copy is there on the machine. Okay. So one of the ideas was that maybe you take a photo of the signed page, then you attach it in that file and you submit it. Because I can tell you now, I will drive to town, meet, then I take reports. It's too risky. So if you have your hard copy, the better. Just be on the waiting. That one will be okay. Recommendation from HR, yes, that will work. Yes, provided they knew you, etc. And yes, I don't see any need for being alarmed. Digital signatures, yes, these ones can actually even work. Okay. Anyway, official communication on IBA still ongoing. I think the next faculty meeting could be in a week's time or something. I've not yet received an email. Then from there now, I will be able to communicate clearly to you guys. Recording for the class, yes. Rebecca, yes, I will upload. Yes, I will. Yeah. Okay, fine. If you have more questions, email remains open. You can call me, etc. And then we'll be able to go forward. So finally, Thomas, for those already supervised by the faculty supervisor, no. Faculty is different from host. We have to find a way to verify on the host side. So still, communication will be given. So either way, as far as machine learning is concerned, it's just revision. It has been a revision week, maths, etc. And then now you can install. That was my next point. Finally, please, these things that we were saying, just listed on the outline. Okay, please, you can go ahead and install these ones. Okay, we had already done Python, ensure it's 3+. You can use either for an account, etc. You can actually install these libraries. We usually say just have them offline, though we'll be working online, Google Call, just in case maybe power is out or something, or you want just to work offline, then upload on GitHub, any of those work. So though we'll be installing all these as we do our notebooks, still it's good to always have these softwares offline. The one that I forgot is the one for computer vision, image processing. You can check out OpenCV and check out how to install it. we can use to do a little bit of image processing. Okay, so if you can just go ahead and do all this before we actually get to the next thing. We'll actually be learning theory. We'll do regression and a lot of the theory behind all these models, etc. So week 2, the work for week 2, week 3, week 4, 5, 6, and 7, because we had gone through this, they will be overlapping. So I will be overlapping as we do a lot of tasks and build some real world kind of models, okay, with some data. So I will be overlapping between all these, so that next, the place I want to land on is first here, okay, and then in deep learning. Here is not like linear, okay, it's like a logistic regression or something like that. Anyway, that has been good. We can now comment with our student numbers as we now go to relax. I hope you stay safe and your lunch. Take care. I'll see you on Friday. Enjoy.